Good morning, everyone. So this is my original title, and probably a lot of you must have been thinking, well, it's going to be one of these boring talks about mathematical niceties, which are irrelevant anyway. And that was the original plan. But, well, since as I've been attending this conference, I thought that it would be even less point of doing such a talk than usual. So I probably expand a little bit on what I was planning to do today. And in fact, what I was planning to do today might actually have disappeared. But well, we'll see how it goes. So the plan is therefore just to discuss some unresolved annoyances when you try to handle black holes in a mathematically rigorous manner, and it actually connects to yesterday's discussion that we had. And then here I'm going to assume any lambda. Then I present you some recent progress in the case where lambda is 0 and also positive. And finally, the negative case was the original plan will come at the end of this talk. So what's all this about? When you're doing mathematical physics and you look at any theory, not necessarily Einstein equations, but could be a geometric theory of gravitation, but anything else, typically what you want to understand is the set of solutions, global properties of solution of the equations. And one usual step is to find time-independent solutions because they give you some hints about what happens. Now in GR, there are two kinds of time-independent solutions. There are strictly stationary solutions where technically you have a killing vector which is time-like everywhere, and you have black hole solutions where the killing vector might actually, well, first will stop being time-like certainly at the event horizon, but might even do it before. So this is something which one has to keep in mind. But in any case, so there's one difficulty compared to, say, Young-Mills or something like that. Well, once you have those, and of course you don't want everyone, but you want the regular ones, but once you have those, you want to understand which one of them are stable or not, and then you might say, I'm happy, or you might say, well, there's a lot more work to do. And for example, in GR, what happens beyond event horizons? Do we have chaotic behavior? Do we have mixed master? Is curvature blowing up or not? Do we have spikes in the curvature? How extendable are singularities? So this is all way, way beyond our current technologies, and I'm just going to talk about the stationary solutions and perhaps mention something about stability. So just to get the technology right, there's static and stationary. Stationary is, roughly speaking, time independent, or at least I am dependent at large distances. And static, you have an extra time reversal isometry. It's not rotating. That's one way of thinking about this, right? Stationary, time independent, rotating, and perhaps rotating, and static is certainly not rotating. Now, there is a notion of degenerate and non-degenerate, which is going to come up, which came up yesterday, and so it's going to come up in the next theorem, so I want to make it clear what it means. But to make it clear what it means is a bit tricky if you have to do with a stationary solution, so let me just tell you exactly what are the features of degenerate against non-degenerate solutions when you're static. Well, first, you don't want any static solution. You want something which is regular. So say, for simplicity, you're going to take solutions which are a product. So you have a time component and a space manifold. And if you are in vacuum, then, well, a static metric will take this form. So you have no of diagonal components. Gamma is a time-independent Riemannian metric. The vacuum equations for the space-time metric reduce to geometric equation for this Riemannian metric. And the difference between degenerate and non-degenerate is the geometry of the thing. if you have a non-degenerate static solution, then this manifold will have a boundary at finite distance at which this function v vanishes. Okay? So that's non-degenerate horizons. And degenerate ones would be a situation where instead of having a boundary at finite distance like that, you have an infinite cylinder going all the way down. Okay? So that's how it looks for static, and for stationary, it's the same spirit. In the known solution, this corresponds to 0 or non-zero gravity, or for Kerr solutions, it would be slow spin or extreme spin. Okay, so, but when you want to formulate theorems, you're not going, well, the extreme terminology is not the best one before you know that you have to do with Kerr. Right? So in your hypothesis, you have to build things which you can just read off from the geometry. So that's degenerate and non-degenerate, and it's going to be confusing at the end of my talk, or the later part of my lecture, because degenerate there will mean something else, but I'm going to explain you what degenerate there means. Good. So this theorem we discussed yesterday, the no-Herr theorem, and now lambda is 0. A lot of people involved, but then you assume you have a stationary solution. It's electrovacuum or vacuum. And there are these hypotheses that I already mentioned yesterday are not that fortunate. You have analytic, non-degenerate, connected, regular, then it's Kerr-Newman. Okay, so there is a theorem. There is a beautiful theorem. A lot of people were involved, and but it has these limitations. And these limitations, one really would like to get rid of them, especially because, for instance, if you assume static, you don't have them, right? So these unpleasant 3 conditions here, you don't need them. So in static, electrovacuum regular is either Reichner-Nordstrom, or MP means Majumdar-Papapetrou. That's a solution where there are 25 black holes sitting there looking at each other without doing nothing. So there's a complete description, and that's the satisfactory version of the theorem. One would like get rid of this thing, these 3 things. So of course, if you're looking at a single black hole, maybe you don't care about this connected business, right? So that's not maybe such a big issue. Although it's really annoying that we cannot show that there are no solutions which have 3 components of the event horizon in vacuum and just sitting there. Every physicist will tell me that, of course not, doesn't make sense. How could they? But we don't know how to prove this. So this connected is annoying. This non-degenerate business is, you'd say, well, non-degenerate is an extreme case. So if you think about this as 0 temperature against non-zero temperature, 0 surface gravity against non-zero surface gravity, then 0 is very special, so it's a very special case. But of course, if you look at the plots that we've seen yesterday, a lot of these black holes seem to have a lot of angular momentum. So maybe they actually are they are extreme rather than non-extreme for some by some mechanisms that we don't understand. We don't understand why they should have more A large anyway, right? So maybe they are extreme, and maybe there are degenerate black holes out there which are not Kerr. Right? Nobody has been able to prove that, except with some extra conditions. Now, the analytic business is also annoying because, of course, this is a theorem about stationary solution, but a real-life solution is not exactly stationary. So we expect that if we have a solution which is not, that a lot of solutions which are will evolve to stationary states, therefore will evolve to these solutions that we have classified. But analytic means that if you know what the metric is in this place of the universe, you know the metric everywhere, period, right? So you just don't even have to think. You just measure what the metric is here, and you're done. Analyticity makes it for you, right? So no place for free will, no place for physics, no place for things happening somewhere out there. It's absurd, right? So there's no reason that this thing be analytic, and then state has no reason to be analytic, and therefore a theorem of the kind I showed you is a nice theorem and a lot of work, but it's not very useful for many purposes. Good. So, well, there is some progress on this issue, and that's a theorem by these three gentlemen, Alexakis, Ionescu, Kleiman. If you are near an on-extreme Kerr, then it is a non-extreme Kerr without assuming analyticity, right? So that is, for many purposes, perhaps as good as one wants. If you have something sitting in a galaxy, in the center of a galaxy, it's been sitting there for a long time. It's been settling down, so maybe it's been settling down to its not very far from an end state, and well, anyway, so we have a theorem like that, and of course one would like to have a more general one. Now this is about analyticity. There's more recent progress concerning the degeneracy condition. I don't have time to explain you what a near horizon geometry is, but these degenerate black holes have some nice properties that you get equations for the metric on the horizon, and that's called the near horizon geometry. And understanding the solution of this equation is the first step to understand the global solution. And so the theorem is that if you have a near horizon geometry, so a geometry on related to this extreme black hole degenerate horizon, and if this near horizon geometry is near an extreme Kerr, so again that's a bit in the spirit of this Alexakis, Ionescu, Kleiman theorem, then it is Kerr. Okay, so if you are near horizon geometry not far from Kerr, then it is Kerr. I'm not going to explain you how you prove this. If you're interested, we can talk about it later. But let's go to the question of stability. Well, lambda equals 0, 25 years ago, celebrated Christodoulou-Kleinemann theorem. Of course, everyone asked at the time, well, what if you have a black hole? Well, 25 years later, this is a theorem announced by Michalis Dafermos, January this year, not published yet. If you have a Schwarzschild black hole, then it's stable under non-linear perturbations, okay? So, well, looks good. You look at this, and of course, that doesn't make sense. That's not possible. A Schwarzschild black hole cannot be stable because you can just add a little angular momentum to it and will become Kerr and stay Kerr. So there is the precise statement which goes with this, that you have the set of all initial data, and in this set of initial data, there is a very precise subset that the authors can define. This subset has finite codimension, as you expect. If you perturb non-linearly, so this is not a linear theorem, right? So we've seen this subset of the initial data. If you perturb your initial data non-linearly, it's going to asymptote to Schwarzschild. If you perturb it off the surface, it's going not to asymptote to Schwarzschild. Okay? So this is a very precise statement, as good as you can get for Schwarzschild black holes. Of course, that's not the final statement you want. You want a stability of Kerr, right? So you want to say that if you start near a Kerr, you are asymptote to some Kerr, or you start near Schwarzschild, you will asymptote to some Kerr, right? So rather than there are, but any case, so that's not published, and well, the question is, will it be another 25 years before we get the right theorem? I hope not, but these are difficult things to prove. There was recently announced in August last year by Jérémy Scheftel, this theorem by Kleinemann and Scheftel. So you take Schwarzschild, black hole, you take an axisymmetric perturbation, which is polarized, so satisfies the polarized condition, then again you have nonlinear stability. So this would be something which is more obvious, because if you're axisymmetric and you have zero angular momentum, you cannot add angular momentum. Does it make sense? Well, in any case, if it's axisymmetric, you start with j equals 0, it will remain j equals 0. So of course, if you, so in this sector where j equals 0, take perturbation in the sector, remaining axisymmetric, you're sure you're going to remain in j equals 0, so you can't asymptote to occur then. And so that's another version here, which is not as general as this one, and but still it's very, very difficult theorems, and none of them are published yet, so the writing down will take time. So I just have two things to say about lambda positive, which presumably is the right value for our universe. 32 years ago, we had a Friedrich stability theorem that de Sitter is stable under nonlinear perturbations. The best result so far concerning black holes here is the theorem by Hinz and Vasi that Schwarzschild de Sitter are stable under nonlinear perturbations. And there is a proviso here. It's stable in the region between horizons. So if I think that most of you are familiar about Schwarzschild de Sitter, there is something called the black hole horizon. There's a called event horizon. So there are obviously a region under the black hole horizon, between the horizons, and above the cosmological horizon. So the stability result here is between the horizons. And there's no full stability result yet, which one expects will come. There's some work by Schlue and Ringström on these issues, but at this stage there's no definitive answer yet. Good, so now we're going to lambda negative. We'll stay there. And the first question when thinking about negative lambda black holes is stationary ones, is to ask yourself, why should I study them at all to start with, since they're probably unstable, right? So there is this Bison-Ostrovsky instability. If you take spherically symmetric Einstein scalar field equations, well, there's numerical work which shows that they're unstable near the anti-de Sitter spacetime. So you can make arbitrarily small perturbations which will create black holes. So this is numerics, and there is a remarkable theorem by Machides, again not written down, which says that, well, you still do spherical symmetry, just because, of course, it's much easier. And you assume Einstein-Vlasov equations, right? So you don't do Einstein scalar field equations, but Einstein-Vlasov. Well, it's easier, right? So it's difficult enough, but it's easier. And he proves exactly the same thing, right? So you start with anti-de Sitter, and you can make arbitrarily small, you can add arbitrarily small amount of Vlasov field to this so that it will going to produce a black hole in finite time. So good, but I mean, of course, this means that these things, spherically symmetric solutions are unstable. Of course, this one has matter in there, and one expects that some to be true without matter as well. There's numerical evidence for this. But then if you take a black hole solution, why should it stabilize the system if it's unstable without a black hole? Well, you're far away from the black hole. This instability might as well persist. I don't know what's the thinking about this? Maybe Gary will comment on this later. But it's not clear to me, right, that maybe these black holes should be unstable as well, stationary ones or static, and therefore, from the point of view of understanding the global dynamics as something nice is not that clear. But in any case, this is a very nice and difficult recent theorem about this case. Good. So now starts what was the original plan of my talk, is the negative lambda stationary global irregular vacuum black holes, or with matter fields. And this is a theorem I proved with Mike Anderson and Erwan Delay some 15 years ago. that there exists an infinite dimensional family of globally regular static vacuum black holes with negative cosmological constant near Schwarzschild antide Sitter, right? So when lambda equals 0, in the static case, it's Schwarzschild period, if it's regular. Here, you have infinite dimensional families of solutions. And these solutions are driven by data at the conformal boundary at infinity. So you have some data. If you assume that the metric at infinity is the one that you usually have for Schwarzschild antide Sitter, you're most likely going to get Schwarzschild antide Sitter. But if you vary this metric, you're going to get other solutions. It's not clear that you get stationary ones or static ones, and indeed you will. That's what we prove in these theorems. And so here, near Schwarzschild antide Sitter, it's actually not for all Schwarzschild antide Sitter, because there is a magical value of the mass parameter, which is called how much they have? No, I still have a few minutes, right? Which is called the Hawking-Page phase transition, where it doesn't work. So outside of this magical value of mass, you can construct a lot of solutions. Well, the new result is the one which I was planning to present you, and I was excited about. This is last year. There exist an infinite dimensional families, say exactly the same, of stationary black hole solutions. Now, not only static, but stationary, and, well, near non-degenerate static solutions. So, again, you start with, say, Schwarzschild antide Sitter, and near this metric, you can construct infinite dimensional families of solutions which are vacuum or which satisfy, I don't know, you can probably, can you see the field equations here? Probably not, right? But so you can do it in vacuum, you can do it with field equations. What kind of field equations? Well, if you could see, you would see that this is either Maxwell or Young-Mills or Higgs or scalar fields or dilatants of your F of R theory. Then there's a lot of freedom here. And so the difference between these two theorems is passing from static and stationary, and this turns out to be non-trivial for black holes. And so this is our theorem. So this is still the same theorem that you've seen before. What are the free data? Well, the free data, as before, you get free data at the conformal boundary at infinity. In the previous case, in static case, you had a static metric at the conformal boundary. Here you get a stationary metric at the conformal boundary. If you're doing vacuum, if you're not doing vacuum but with matter fields, you have asymptotic data for the matter fields at the conformal boundary that come in and allow you to construct solutions which are stationary. So good. So now there is this non-degenerate notion, and I warned you that you're going to be confused because this one has nothing to do with the horizon being extreme or not. It means that there is a specific operator which has no kernel. Okay, and this specific operator is called the Lichnerowicz Laplacian, and it's not the Lichnerowicz Laplacian of your metric, but it's a Lichnerowicz Laplacian of an auxiliary Riemannian metric you're going to build for your problem by something called wig rotation, right? So now this non-degeneracy theorem property is actually non-trivial to establish, but we proved it for large classes of metrics which take the familiar form. This would be your usual Schwarzschild antide Sitter metric sitting here, but then you can be in any dimensions, and this metric H, well, could be a metric on a two-sphere that would be Schwarzschild antide Sitter from the freshman general activity, but any space form metric here in any dimension works, and we can prove that there are large classes of such metrics which satisfy this non-degeneracy condition. So the reason I wanted to talk about this here, and the reason I like to talk about this to the mathematical physicist audience, because the method is rather cute. Because to construct this solution, you do this weak rotation business where you replace t by a complex time coordinate, and this, this is a trick which mathematically, where I've always found very strange. But in this case, it turns out that you can really use it to produce elliptic equations. Elliptic equations for complex tensor fields. So the construction is you're producing one parameter family of complex vector field, complex tensor fields, parameterized by a complex parameter I, and you'd show that in a specific, when this parameter has specific values, you're going to get Lorentzian metrics which are real valued. Okay, so you're constructing complex valued tensors, which you'd like to call complex valued metrics, but of course doesn't make sense because a metric has some signature properties or stuff like that, which don't make sense if you have a complex valued object. But then you just right. So the procedure is just to do this weak rotation and then obtain elliptic equations for this complex values object, and then use this non-degeneracy condition. This non-degeneracy condition gives you uniqueness properties for your solution of the equation, and then you can show that the things that you have constructed on this weak rotated side are time independent. They are holomorphic in this funny parameter A that you introduce, and they are real valued and Lorentzian for real A after you undo your weak rotation. If I understand correctly, my time is up. So good. So thank you very much for your attention.
Thank you. Any questions?
Fascinating talk. I have lots of questions I'll ask later. But at the end, when you talked about this infinite family of static and stationary black holes in ADS, can I think of this infinite family as really one black hole but with a lot of hair? Are these boundary conditions that you are applying at infinity just extra parameters or hair?
There is, there's extra information at infinity. So yes, you may think of this like that, right? There's an infinite number of hair at infinity that.
Right. But can I then take the limit lambda going to 0?
It's very singular in this setup.
Okay, so you can only do it for negative lambda.
I don't know how to do this. Lambda has to be negative.
Has to be negative, okay.
Gaston and then Gary, okay.
Okay, so first of all, with regard to the stability of black holes and anti-de Sitter space, so what Bison and his collaborator showed was that because anti-de Sitter space is like a confining box, you put a little bit of energy in there, and it just sort of bounces off infinity, goes through the origin, bounces off infinity, and after it does it many, many times, you can produce small black holes. But if you have a black hole in the space-time, every time it bounces off infinity and passes through the center, the black hole can absorb some of the energy. And so that can damp out the wave, and so black holes are not necessarily unstable, even if the
but then my answer would be, but maybe it doesn't absorb enough of it, so that there will be
right, maybe, but we also, so some of us looked at that, and another argument for the instability is that all the normal modes in anti-de Sitter space have frequencies which are integer multiples of a given frequency. So that makes a lot of resonances when you try to include nonlinear effects. The minute you put a black hole in there, the spectrum of the perturbations doesn't have that resonance, all those resonances, and it looks like you don't have enough. I mean, it's not a proof of anything, but it's evidence that they may be stable.
Any more questions? Okay, let's thank Piotr again for this talk.